All right, so picking up where we left off in the last video, and I think maybe I had mentioned that I was going to do 3 examples, but for the sake of time, I'm actually just going to do 2. I don't think any of you guys will mind with that. So let's look at our second example. So we are in these videos talking about rational root theorem, and talking about how to use the rational root theorem in order to test to see if with any individual possible rational roots, do we get a remainder of 0? And if we do, great, it works. If we don't, we toss it out and we move on to the next one. The whole idea of this is to see if we can get a completely factored form of a function. And if we do, then we're good to go, and then we can graph it. So for our next one, let's see. Here's what we're going to try. Let's go g of x equals 2x to the fourth plus 3x cubed minus 12x squared minus 7x. And at the end of all this, we'll have a plus 6. Okay. All right, so a couple things that are different on this one compared to the last one. First and foremost, there's a number other than a 1 out at the front of this. Okay, there's a 2 this time. And also, this one is raised to the 4th power, not raised to the 3rd power. And just a hint, when it's raised to the 4th power instead of the 3rd power, usually, not always, but most of the time, that means that we are going to have to do the rational root theorem multiple times. So we'll talk about how to approach that here on this problem. But let's begin by just setting up our list of possible rational roots. Remember, what we do is we take all of the factors of the constant. So it's going to be 1, 2, 3, and 6, and divided by all the factors of the leading coefficient. All the factors of 2 would be 1 and 2. So what does this mean? This means we've got a lot of different things here. We got plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 3 over 1, plus or minus 6 over 1. But additionally, we also have plus or minus 1 over 2, plus or minus 2 over 2. However, you'll notice this is the same thing as plus or minus 1. So really, this doesn't add anything new to the list. Plus or minus 3 over 2, and plus or minus 6 over 2, which you'll also notice that 6 divided by 2 is 3. So that's the same thing as this one. So this one doesn't add any more to the list either. However, that 2 on the bottom does add plus or minus 1/2 and plus or minus 3/2 to our list. Most of the time, and I'd say for every single problem that I give you, you're not going to have to get to the point where you're testing fractions in order to use the rational root theorem correctly. But you will see that sometimes you will get those fractional answers at the very end of the problem, and I'll talk about that when we get to it here on this one. Remember, our strategy is let's start with the easiest numbers to test first, and you don't have to make that giant list like I just did as long as you write this down. This will be fine because you can think about what they are based off of this list. So again, our idea here is going to be, well, let's test like x minus 1, then let's test x plus 1, and then from here we could do 2 over 1, so that would be testing x minus 2, and then we can test x plus 2, and then we can test x minus 3, and so on and so forth. Okay, so we want to go in that order. I'm going to be strategic about this because we'd like to try with the easiest numbers first, and we can work our way to the harder numbers as we go. So let's say that we wanted to begin on this problem by testing x minus 1. Okay, so I'm going to try x minus 1 first. I'm going to put a 1 in the box. And across the top here, 2, 3, negative 12, negative 7, and 6. And I'm just going to try my synthetic division here. Remember, we add in the middle. All right. So this would be a we do not get a remainder of 0, so x minus 1 is off the board. Let's try x plus 1 next. Okay, so I'm going to put a negative 1 in the box. Same coefficients. And let's see what we get. Sometimes you're going to need a lot of paper here. I have other students that will erase what they have every time. And if you do that, that's perfectly fine as well. Negative 1 times negative 13 is 13. Excuse me, 6, negative 6. All right. So it looks like x plus 1 is pretty good for us here. Okay. X plus 1 gave me a remainder of 0, which is exactly what I wanted. So let's check this out. when I'm done here, let's collect all of our thoughts. I just divided by x plus 1. That worked. And then I have this remaining answer here. This was an x to the 4, so this is going to be an x cubed. So let's write that down. This is going to be 2x cubed plus x squared minus 13x plus 6. Okay, now there are times where this remaining 4 terms can be factored by grouping. But just glancing at that, I can already tell that that cannot be factored by grouping. You could try for yourself if you'd like. But if this can't be factored by grouping, guess what? I'm going to have to use the rational root theorem again. Or, if you remember this, we call this repeated synthetic division. Okay, repeated synthetic division. So I'm just going to continue trying some synthetic division. Now, I get the question from a lot of students, do I need to make this a list again? Well, guess what? If you try this list again, you're just going to get the exact same list that we already got at the beginning, factors of 6 divided by factors of 2. So you don't need to create a new list. Okay, you can stick with the same list that we were already using. So if you'd like, you can think back here. So we're going to use the same list that we had at the beginning of the problem. We're just going to keep progressing through this list. Now, another big question that I get is, do I have to start back over in the list? Well, guess what? If x minus 1 didn't work the first time around, it is not going to magically work later on. So I don't have to try x minus 1 again. It's already off the board. Now, I could try x plus 1 one more time if I'd like, in case it shows up multiple times. I usually don't encourage that, though. I would just say keep on moving on with your list. We tried x minus 1. It was a no. We tried x plus 1. It was a yes, so that's good. The next thing in our list would be 2 over 1, so that would be x minus 2. So I'm going to actually try that next. Oops, sorry, actually, I'll leave that there just for the notes. So I'm going to try x minus 2 next, but I'm not going to go back to the original function to do this. I'm going to keep what I got as my answer right here, and I'm going to try x minus 2 with that. So let's go ahead and give that a shot. So I'm going to try x minus 2, which means I'm going to put a 2 in the box, and we're going to use this right here for my coefficients, and we'll see what we get. So this is going to be 2, 4, 5, 10, -3. Remember, I'm adding in the middle, -6. And when I'm done, guess what? I get a remainder of 0. Yeah. Let's go. All right, so once again, let's collect our thoughts and let's see where we are at. So number one thing I see people forget, don't forget that originally we divided by x plus 1 and it worked. That does not just magically disappear. It's still there. Then I divided by x minus 2 and that worked. And then I had this left over. Okay, this was an x cubed, which means this is an x squared. So this is going to be 2x squared plus 5x minus 3. Remember, the whole idea here is to get ourselves down to a quadratic because we can do lots of stuff when it comes to quadratics. So let's give that a shot. We're going to see if we can factor that quadratic. So I'll keep the x plus 1 and the x minus 2. Okay, and then with this quadratic, I'm going to begin by putting a 2x and a 2x. Okay, I'm looking for factors of 2 times -3. That's -6. That add up to positive 5. Those two numbers are going to be positive 6 and -1. Okay, so I'm going to put a plus 6 and a minus 1 right here. Now remember, we want to make sure that we factor this correctly. Currently, 2 times 2 is 4, but I need it to be a 2. So I'm going to divide a 2 out of this first set of parentheses in pink here. So when I'm done, here's what I'm going to have. X plus 1 times x minus 2 times x plus 3, 2 divided by 2 and 6 divided by 2. And then I'll have a 2x minus 1 left over. This is completely factored. Okay. What did we do to completely factor this? Well, we had to use synthetic division one time, and then we used synthetic division a second time to get myself to my final answer. Continuing to use the rational root theorem and just picking up in my list where I left off, and I got myself to this final factored form here. So let's try it to see if we can graph this. So multiplicity here, 1, 1, 1, 1. I'll add them all together, I get 4. So this is even, and this is positive. This matches up exactly with what I had at the beginning of the problem when the highest power I saw was 4 and this function was positive. Remember, whatever you start with should end the same way, and if it doesn't, it means you lost track of something along the way, and you got to go back and figure out where that's at. most of the time that will come from people not writing this first factor down as they continue on in the problem. And I'm sure I'll mention that now, and then students will still make the same mistake when you guys take the quiz here at the end of the unit, but I'll try and mention it as often as I can. So this is even and positive. Okay, that's going to be up and up. Let's think about our x-intercepts for a moment. This would be x equals -1, 2, -3, and 1/2. All right, so I'm going to make a little note here, and I did not do this on the first problem, but you'll notice that the same thing applies on the first problem. If I take this list right here, and I put it right next to these x-intercepts, what I want you to notice is that there are no x-intercepts that we just got as an answer that don't show up in this list, okay? So for example, -1, well, that's 1 divided by 1, so that checks out. 2, that's 2 divided by 1, that checks out. -3, well, that's 3 divided by 1, that checks out. And then 1/2, well, that's my fractional answer, which comes from this 1 here divided by this 2 here. So everything that I'm getting as an x-intercept shows up in that original list of possible rational roots. Remember, that original list is possible rational roots, not actual rational roots, but all of the actual ones that I get at the end showed up in that list. Okay, so everything's looking good. Last but not least, let's go ahead and draw our graph. Again, this gets a little redundant because it's all kind of the same stuff every time. None of the graphing rules change throughout this unit. So we got -3, -1, 1/2, and 2. Let's draw in our end behavior. We're going to be up on the left, up on the right. Now, we have not seen any repeated factors yet. In terms of like you got an x minus 2 and then another x minus 2 or something along those lines. We haven't seen that yet in these two examples, but it could show up as you're trying some on your own. All of these, though, are to the first power, so that just means we're going to go straight through at each one. We get a nice W-shaped graph when we're finished, okay? So straight through at all of our x-intercepts. And again, the reason why that's the case is because these are all to the first power, and if we're to the first power, we go straight through, okay? All right, so this is called the rational root theorem. I'm not including any more practice for today in the OneNote. However, if you do want to get started on the worksheet practice for class tomorrow, feel free to do that. The link for that is in the Google Doc, but you will also work on it in class tomorrow, and I will have those solutions posted in the OneNote folder. Hope you guys have a wonderful rest of the day. I'll talk to you later. Bye, guys.